To last class, we have studied about the bending stresses in the beams. Bending stresses in the beams. So today class, we will study about the shear stresses in the beams. So how the shear stress is developed in the beams. So in the previous topics, we are studying about the shear force. We are studying about the shear force, shear stresses in the beams, topics to be covered. మనం shear stresses, shear force చదివాం. So అదేమో individual component మీద. Now we will study about on the beams how the shear stresses can be calculated. How the shear stresses are calculated. So our topic is how the shear force is applied on the beams. Next, how the shear stresses can be calculated in the beams, and how the horizontal shear stress is developed in the beam. Next, derivation for the shear stress, and shear stress distribution for the different cross sections, and some problems. So how the shear force. So already we have discussed about the shear force, the force which is acting tangential to the area, which makes to shear the component, Shearing means we need to tear it. So example is a tire is moving on a road, or you are tearing a paper, a paper is there, you will clamp on one side and another side, you will twist the paper, so it will be cutting like this. So it is nothing but a shear stress. Shear force is applied on the paper. So here the shear force is mainly shearing force, so it makes to shear the component. So here, wherever we have discussed, wherever the shear force is applied, a complementary shear forces will be developed on the other sides also. So what is shear stress? So here shear stress is represented by tau. And it is nothing but a ratio of shear force by cross-sectional area.
Sir, resound.
The stress is nothing but force by area, Every time it is force by area, but here it is a shear stress. Therefore, shear force is coming into picture. By area. So here, if I consider a body, now this is the shear force which is acting on the tangential to the area, Therefore, this is the shear force by area. I need to consider to calculate the tau, that is nothing shear stress. Again, the units for the stress is again Newton per meter square. Newton per meter square is the stress units. So here an example is shown here. A body is considered here and force is applied tangentially to the body. This is the force. Shear force is applied tangential to the body. Therefore, at this cross section, we will get a shear stress. So here the area will be B into D. B into D is the area. B into D is the area, and the force is shear stress. So shear force. Yes is the shear force. Next, if you consider the beams, the cross section of beams may be a square, a T section, a I section, or a C section. That is channel section, we will call it as the channel section. So this may be a cross section of the beams. So here we will have a neutral axis and neutral layer. We will have a neutral axis and a neutral layer. So at the neutral layer, we will have maximum shear stress. At the neutral layer, we will have maximum shear stress. When we are moving, here we will have a maximum shear stress. When we are moving away, to the topmost layer, the stresses will be decreased. So at the topmost layer, the shear stress is 0, and the bottommost layer, the shear stress is 0. So it will be maximum at the neutral axis. If you observe the bending stress equation and bending stress, it is quite opposite. The shear stress is maximum at the outer layers for a bending stresses, and it is 0 at the neutral layer. So it is quite opposite amount. The shear stress is a maximum at the neutral layer, and it will be minimum, and it means it is reducing its shear stress while I am moving away. It reduces its shear stress value, and at the maximum Y, it will be 0. So yeah, if I am considering a beam, and the shear force is applied on the beam, due to the shear force, a parallel shear force will be developed, that is shear stresses will be developed on the cross section of the beam on small fibers. The shear force is applied in this direction, and to resist it, a shear stress is developed on the cross section on small fiber. He is showing the small fiber here on the beam. So shear force is applied on the beam, and a parallel shear force will be developed, and shear stresses will be developed. So we have studied that this is the shear stress while we are applying the external force which is moving downward direction. We have studied that if one side shear stress is developed, automatically a complementary shear stress will be developed on the component. Therefore, this side also the shear stress will be developed. This shear stress will be called as horizontal shear stress, and this shear stress will be called as vertical shear stress. So if I consider a beam whose length is like this, and I am applying the force in this direction, due to this force, a shear force will be developed in the component like this. This is vertical shear stress. Vertical shear stress, and another shear stress also will become developed here. A horizontal shear stress will be developed on this face. So we'll have vertical shear stress as well as horizontal shear stress. So we will derive a derivation for the horizontal shear stress in the beams. Horizontal shear stress in the beams. So derivation. So here a horizontal shear stress need to be developed and we need to derive it. We need to derive it. So here I am considering a beam. I am considering a beam whose length is L. And I am considering a small element. And a UDL is applied on the beam amount. And a UDL is applied on the beam. I am considering only small element whose length is dx. So this is the length of dx. I am considering length of dx. I am concentrated only small element only. So on this face, on this side we have shear stress as S. Shear stress as S. On this side, the shear stress will be S plus delta S. S plus delta S. The shear stress will be S plus delta S. And the bending moment at this side is M. And the bending moment at this side will be M plus delta M. That is, we'll call it as dm. So here discussing about this side is AB. I am considering this side as AB and this side as CD. So two cross sections AB and CD at a length of dx. This is AB side and this is CD side. So on the side of A we have M and S, where M is the bending moment and S is the shear force. And on the CD side, we have a shear force of S plus delta S and bending moment as M plus delta M, because a UDL, due to the UDL, the bending moments will be varying in the small length also. The bending moment will be varying in the small length also. So this is the diagram is showing a simply supported beam and a UDL is applied on it, and the cross section is AB and CD is another cross section. This side, the M is the bending moment. In the section of AB side, the bending moment is M and shear force is S. And other side, at a CD cross section, the bending moment is M plus dm and the shear stress is shear force is S plus delta S is the shear force. Now I am considering a small area, this small length which is at a height of y1. So this is the green color. This is the neutral axis. This is a neutral layer. From the neutral layer, that is, this point is on the neutral layer. So I am considering this as y1. I am considering this as y1, and the topmost layer from the neutral axis is y2. So from this point, neutral axis, from the neutral axis, the green color begin, that is hatched line. Here in the diagram, it is a hatched line. The green color begins at a distance of y1 from the neutral layer. And the topmost layer distance from the neutral axis is a y2. And I am considering a small fiber. Cylindrical fiber is considered here, Cylindrical fiber is considered here. We can see the diagram. A cylindrical fiber is considered whose area, the cross-sectional area of the cylindrical fiber is dA. The cylindrical cross-sectional area, circular area is dA. Now, we have observed from the bending stress, there will be stresses in the beams. If I consider a simply supported beam, the topmost layer feels a compression and the bottommost layer feels a tensile. So here the fiber, topmost fiber means it feels a compression. The fiber feels a compression. So here the force will be a compressive stress will be developed here. Compressive stress will be developed because above the neutral layer, and it is a simply supported beam. Above the neutral layer and it is a simply supported beam, therefore we get a compressive stress on the fiber. Let us consider a cylindrical. So here is considering a cylindrical at a distance of y from the neutral axis. So the height of the cylindrical axis is y. We have here y1, y2 and y. y1, y2 and y. Now, if I need to find out the stress on the cylindrical body, so I have a formula. Stress is equal to, bending stress is equal to, that is in the side of AB. In the side of AB, therefore the stress will be sigma only. The stress will be sigma only. So it is a sigma. On this face, in the side of CD, the stress will be increased stress because the bending moment is increased. The bending moment is increased. Therefore, we'll have D into delta. That is some increased stress on the other face, CD face. So we have the stress equation. That is nothing but M by I into Y. The axis is from the neutral axis, it having a distance of Y. Therefore, the stress can be calculated by using the formula what we have proved in the last classes, M by I into Y. So that is the stress on the side A, B, on the fiber. We are considering only fiber now. Similarly, the stress on this side is sigma plus D sigma. So to calculate this value, so M plus dm, here M will be incremented. The M will be incremented by Ixx into Y again. This is the stress on this face. This is the stress on this face and this is the stress. So here we calculate the stresses. So this is a sigma, this is sigma plus D sigma. Now I need the force on this face. I need the force on the face AC. So to calculate the force, I know the stress now. I can calculate the stress now. Therefore, force is equal to stress into area. Stress into area. The area of the fiber here is dA. The area of the fiber is dA. Therefore, I can calculate the force on the face AB side and the force on CD side. So the stress on the CD side is sigma plus d sigma into dA again. The area is same amount. The area is same on the both sides. The fiber having the same area. The fiber having the same area. Therefore, the forces is known value now on the fiber. Therefore, I need to find out the net force. I need to find out the net force. So two forces are known now. So I need to find out the net force. So here the force on the C is somewhat higher. CD side is somewhat higher than the force on the AB side. Therefore, force on CD minus force on AB gives the net force that is applied on the fiber. So this is the fiber and I need the net force. Net force which is moving this side. Which is moving this side. Now, after finding the net force, I need to find out the in terms of bending stresses. So here I have substituted the bending stress equation for the, this is nothing but a AB and CD. This is the horizontal force. This is the horizontal force amount. So this is the horizontal force which is moving in this direction. So this is the horizontal force. But you are vertical direction, but a shear force is developed here in between a green cross section and a blue cross section. Blue cross section key, green cross section key, a shear force will be developed here. That force is called as horizontal force. So here I am applying in terms of stresses and I have substituted in terms of bending moment. Therefore, M and a negative M will be cancelled. So we are getting a dm by I y into dA is the force, horizontal force which is applied along the green direction. Along the green direction. So this is only on the fiber. This is we have calculated only on the fiber. But I need a total force. E fiber ద్వారా వచ్చిన force మాత్రమే ఇది. సో ఇలాంటి ఫైబర్స్ నేను గ్రీన్ లో చాలా ఉండొచ్చు. ఇలాంటి ఫైబర్స్ గ్రీన్ లో చాలా ఉండొచ్చు. So I need to cumulate all these fibers in the green cross sectional area. In the green cross sectional area. So I am considering a layer EF. So this green color E and F అనుకుంటున్నాను. Green color పైన ఉన్నదంతా EF. Green color line EF line అనుకుంటున్నాను. So పైన ఉన్న area. Let us consider ABCD. That is ఇది ABCD. This is the cross section. And కింద EF అనే line. A cross section EF line paina. So EF is lying at a distance of y1. Already discussed chesama. So EF on a line y1 distance lo undi anukuntunanu. Now the cylinder area is dA. Now I need to find out the all forces developed that type of fibers. ఇలాంటి ఫైబర్స్ వల్ల EF పైన ఉన్న ఏరియా అంతా, దట్ ఈస్ గ్రీన్ కలర్ ఏరియా అంతా, సో విల్ హ్యావ్ ఏ ఫోర్సెస్, సమ్మేషన్ ఆఫ్ ఫోర్సెస్. ఇలాంటి ఫోర్సెస్, ఇలాంటి స్మాల్ ఎలిమెంట్ మీద చేసాము, స్మాల్ ఫైబర్ మీద చేసాము, అలాంటి ఫైబర్స్ EF అనే లైన్ పైన విల్ హ్యావ్ ఇన్ఫినిటీ. That is, we can calculate by considering small elements. So this is the diagram, small diagram for understanding. So this is the fiber. And this is the area. We need to calculate, and this is the Y1, and this will be E and F, and this is the Y2, that is the topmost layer distance. So horizontal force is equal to ilanti elements, fiber elements naku Y1 kandi outermost YT daka, that is here Y1 or Y2 or YT edana anukochu, I am considering as Y2. So I need to add the small forces. ఇలాంటి ఫోర్సెస్ అన్నిటిని నేను యాడ్ చేయాలి. సో ఫ్రమ్ ది బాటమ్ లేయర్ టు టాప్ మోస్ట్ లేయర్, దట్ ఈస్ EF లేయర్ కాండి టాప్ మోస్ట్ లేయర్ దాకా కూడా నేను యాడ్ చేయాలి. అలాంటి ఫోర్సెస్ అన్నిటిని యాడ్ చేయాలి. సో ఇలాంటి ఫోర్సెస్ F1 ఒకటి వస్తుంది, F2 ఒకటి వస్తుంది, F3 ఒకటి వస్తుంది. సో ఐ నీడ్ టు యాడ్ ఆల్ దిస్. సో స్మాల్ ఫైబర్స్, ఇలాంటి ఫైబర్స్ ఎన్ని కన్సిడర్ చేస్తే అన్ని వస్తూ ఉంటాయి. అన్ని ఫోర్స్ని నేను యాడ్ చేయాలి. సో అన్ని ఫోర్సులు కలిపి విల్ గెట్ F horizontal total. So here it is a constant, బయటికి ఇది మారదు కాబట్టి dm/I బయట తీసాము into x and summation of y turns 1 to y2 and y into dA. సో మనకి ఇంతకు ముందే చదివాము, sigma of y dA is nothing but y bar into area. So అంతకుముందు చదివాము y bar is equal to summation of ai yi by summation of area. So here we are getting the shear, horizontal shear force. Total horizontal shear force is equal to dm/I into y in y bar. It is y bar into A. Here y bar is nothing but the shaded area, the cross-sectional area centroid. ఎందుకంటే ఇలాంటి స్మాల్ ఫోర్సెస్ అన్నిటిని, this is the cross section, చిన్న ఫోర్స్ F1, F2, F3 are the forces developed above the EF line. ఇలాంటి ఫోర్సెస్ అన్ని డెవలప్ అయినాయి అమ్మా ఫైబర్స్ మీద. సో ఈ అన్నిటిని కలిపి నేను ఒక పెద్ద ఫోర్స్గా మార్చేసుకోవచ్చు. which is need to be concentrated on the centroid, of the cross sectional area. So EF line paina cross sectional area ki centroid meeda ee force anta act avutundi. EF line paina centroid point meeda ante ee cross sectional area ki centroid, that is a point I have shown here ma. This is a point of the centroid. So it is a rectangle and this is the centroid point. So at the centroid point, the force is accommodated. The force is accommodated. The net force is accommodated. So here y bar is the distance of the centroid, is this distance of the centroid of the cross-sectional area above the EF line. EF line paina centroid distance. If I consider this cross-section, this is the neutral axis and this is the centroid for the cross-section, and this is the area I am considering. This is the EF line, and I need the centroid of this cross section from the neutral axis, that is y bar now. ఈ ప్రాబ్లమ్స్ లో కన్ఫ్యూజ్ అయ్యేది ఏంటంటే ఇక్కడ ఒక y బార్ వస్తుందమ్మా, ఇక్కడ ఒక y బార్ వస్తుంది, అది న్యూట్రల్ యాక్సిస్ కనుక్కుంటాక మాత్రమే, ఆ తర్వాత దాన్ని మర్చిపోవాలి మీరు. న్యూట్రల్ యాక్సిస్ కనుక్కుంటాక మాత్రమే y బార్. తర్వాత ఇండివిజువల్ క్రాస్ సెక్షన్స్ కి EF వేరీ అయ్యే కొద్దీ, EF వేరీ అయ్యే కొద్దీ, EF లేయర్ వేరీ అయ్యే కొద్దీ y బార్లు మారిపోతూ ఉంటాయి, y బార్లు మారిపోతూ ఉంటాయి. So here I need to consider this small area now. This is the area. Shear stress kaval now. So this is the width D. This is the width of the beam, and the length of the beam is I have considered as dx. Consider a small element, and the force applied here is F horizontal. F horizontal is the force applied on this. So here I need to find out the shear stress in between green color and blue color. I need to find out the shear stress in between green color and blue color. Therefore, shear stress tau horizontal is equal to shear force horizontal by area is B into dx. B into dx is the shear stress developed. Shear stress developed on the in between green and B. Green color beam meda and B gun, that is nothing but above the EF line. Above the EF line. Above the EF line ema. This is the EF line. EF line paina force create avutundi. So that is the force, horizontal force. Now I need to find out the shear stress. Horizontal shear stress is my aim. Horizontal shear stress is my aim. So I need to find out the horizontal shear force by area. So that is the area is B into dA. B into dx sama. B into dx. So here B into dx is the area of horizontal cross-sectional area. Now horizontal shear stress is equal to horizontal shear stress is equal to horizontal shear force by shear resisting area. Shear resisting area here is, we have discussed, that is B into dx. That is the area. Shear resisting area. If I consider the small element. If I consider the small element, and we have considered the whatever the force, net force applied, that is nothing but dm by I into a into y bar is the force applied on the centroid above the EF line. That is a horizontal force. So I can write it as dm by dx, dm by dx into this is a capital A, that is the area, cross-sectional area, that is a green color area ma, into y bar into ixx into b. B is nothing but width of the cross section. Width of the cross section. Now, in the previous class, we have studied the relationship between the bending moment and the shear force. So we have derived that shear force is equal to dm by dx. Therefore, shear force S is equal to dm by dx. Therefore, substituting in my equation, shear stress is equal to S is the shear force, area is the green color area, and y bar is the distance of the centroid above the green color area ma. That is above the EF line. Above the EF line, I need to find out the centroids. That is the y bars now. That is y bars from the neutral axis. I need to find out the y bars from the neutral axis. And Ixx is the moment of inertia. Ixx is the moment of inertia about the xx, and B is the width of the beam. B is the width of the beam. So this is the shear stress developed. That is nothing but horizontal shear stress developed on the surface in between green and blue. Green and blue. So in between the area, green and blue areas majlo is the horizontal shear stress developed in the body. So this is the only equation. This is the only equation in this chapter. This is the only equation in this chapter. So we need to derive some standard cross sections and its diagrams of shear stress. So here it may ask for the 2 marks. So for a rectangular cross section, so at the neutral axis we'll have a maximum shear stress at the topmost layer. At the topmost layer we'll have a shear stress as 0, horizontal shear stress as a 0. And the bottommost layer will have a horizontal shear stress as 0. For a circular cross section also, at the neutral axis, we have a maximum shear stress distribution, and it will be varying while the distance EF layer is varying. Yes, EF layer is varying. At the topmost, it is 0 again. We need to derive it and we need to draw it. And for a triangle also, it will be same. It will be like a parabolic. And for a hollow cross section, the shear stress is maximum at the neutral axis, and it will be varying up to this point, and at this it will be 0. This is the baseline now. This is the baseline. And for a hollow rectangular cross section, the diagram will be somewhat like a D. So up to here it will be curvature and again a curvature. We can see a vertical line. We can see a vertical line at this point. The stress is increased. The stress is increased directly. So here also we can see a vertical lines up to certain limit. Vertical lines up to certain limit. The stress will be differ at this point. So this is the C section, we will call it as channel section. Channel section. So it also looks like this only. It also looks like this only. So next I, that is H cross section. H cross section, it looks like this. And a T cross section. T cross section, it looks like this. So it may ask for a 2 marks. So different types of shear stresses diagrams along the cross section. He may ask for the 2 marks. Draw the tendency of a diagram while the y is increasing. Along the y is increasing along the cross section for a shear stress diagram. So we need to draw a tendency of a shear stress diagram along the cross section. So this is the fundamental for the shear stress. This is the fundamental for the shear stress. So we need to do some derivations, small derivations, 3 derivations. And next we need to do some problems. So the problems need to be continued, and the derivations, small derivations, that is how we are getting the curve for a rectangle, for a circular, and for a I section and a T section, and for a triangle. So we will show the curves and derivations. We will show the curves and derivations, how we are getting these curves and derivations for the rectangular cross section, for the circular cross section, and for the triangular cross section, and for the I cross section, and for the T cross section. So 5 different cross sections. I will show how we are attaining the curves by deriving it. And only one problem will be solved each and every cross section. So I will solve a problem on a rectangular cross section, and a circular cross section, and a triangular cross section, and I section cross section, and a T section cross section. So 5 different problems with the derivations will be continued in the next classes. So with this I am concluding the section. My assignment ఎంతమంది రాయలేదు రాయాలి.